My name is Ludo Fraser-Taliente. My poster is about a recent paper in which we demonstrate that for a broad range of large N quantum field theories, their conformal infrared fixed points are determined by a simple constrained extremization principle on the number of effective degrees of freedom of a mean field theory. Now, any large N field theory is expected to be a mean field theory, i.e. purely Gaussian, albeit with non-trivial scaling dimensions, to leading order in N. This is thanks to factorization. However, here we demonstrate that essentially the infrared theory is completely determined by an extremization of the number of degrees of freedom. So, specifically, this family of melonic CFTs includes the SYK models and their generalizations, the vector models, i.e. ON, Gros-Neveu, etc., and the tensor field theories. So if our goal is to calculate the IR conformal field theory data, specifically the scaling dimensions delta, in our paper we demonstrate that for a large N QFT of this type, with some given field content, the IR is simply a mean field theory with the same field content. The aforementioned non-trivial scaling dimensions are then completely determined by an extremization of the number of infrared degrees of freedom, subject to a linear constraint saying that the interaction Lagrangian must be exactly marginal, i.e. it has to survive to the IR. Crucially, this result does not depend on the complicated details of field global symmetry representations and interaction terms. It suffices to know only the schematic form of the interaction potential. In particular, the precise function that we extremize is the universal part of the sphere free energy of a mean field theory, i.e. the logarithm of the partition function evaluated on the sphere. Now, if you want exact results in quantum field theory, there are generically two places you might look. The first is supersymmetry, and the second is large N. We have known for 20 years, since the works of Intrigligator, Wecht, and separately Jafferis, that the exact superconformal scaling dimensions extremize the universal part of the sphere free energy F. These are the procedures called A and F maximization respectively in 4 and 3 dimensions. Therefore, I'm telling you today that the same mechanism arises in large N, beyond supersymmetry, in generic dimension D, without any supersymmetric localization, and we explicitly construct and interpret the function F. The universal part of F has been conjectured to essentially count the number of effective degrees of freedom in continuous dimension. This is because it interpolates between the known Zamolodchikov C functions, which are C in 2 dimensions, F in 3 dimensions, and A in 4 dimensions. This permits the interpretation of our result as an extremization of the number of infrared degrees of freedom, but now extended to continuous dimension in the spirit of the generalized C, F, and A theorems. We can establish this result using the two-particle irreducible effective action, or equivalently by Feynman diagram resummation. Essentially, the disorder average in the SYK case or the index structure in the vector and tensor cases conspire to truncate the form of the effective action. This allows us to make the identification of this effective action with the action of a mean field theory. The complex IR structure of these models can therefore be straightforwardly understood as resulting from this extremization principle. The outcome is a classification of the melonic CFTs. They are the conformal mean field theories which extremize the number of IR degrees of freedom, subject to a marginality condition on that interaction Lagrangian. For more details, please come and chat or refer to the paper now in the archive.